Welcome to today's video where we'll be exploring the fascinating world of energies in steady fluid flow. In fluid mechanism, understanding the different forms of energy involved in fluid motion is crucial to grasp the behavior of fluids in various scenarios. So let's get started. The first type of energy we'll discuss is kinetic energy. Kinetic energy is the energy possessed by a fluid element due to its motion. So if you have a body with some mass and it's moving at some velocity v, that body of mass has kinetic energy. Now in the context of fluid flow, it's given by the formula kinetic energy equal to now this will be your kinetic energy. This will be the mass of the fluid, and this will be the velocity of particles. Now, if I take the mass here and I substitute with the formula of the density, and I say now my kinetic energy is given by 1/2, and instead of mass, I rearrange this formula to substitute for mass. That will give me density and volume, and I still have my velocity squared. Now from this equation, you can see that kinetic energy is directly proportional to the fluid's density and the square of its velocity. Now, if all particles are moving at the same velocity, let's see what is our kinetic energy in terms of unit weight. I will take my kinetic energy, divide by my unit weight. Even with the formula here, 1/2 density volume velocity squared over my unit weight. Now my weight is given by W. Now instead of taking W and putting it in here, I'm going to rearrange this equation and substitute for W, and that gives me specific weight times volume, rearranging this formula here. Now you can see that the volumes will cancel, and my kinetic energy per unit weight will be given by 1/2 density velocity squared over specific weight. Now again, I want to substitute for this weight and rearrange this formula and substitute density times gravitational acceleration. Now you can see that the densities will cancel each other and I will be left with gravitational acceleration. The point I'm making is that my kinetic energy per unit weight will be given by 1/2 velocity squared over gravitational acceleration, and rearranging this formula, it can be v squared over 2g. Now I've written it in this way so that my units give me meters. For reasons I will explain later, you will see why I'm putting it in meters. Now this equation will give us our kinetic energy in meters as reference to unit weight. Next up, we have potential energy. This form of energy arises due to the position of the fluid element with respect to some reference level. So if you have some body that has mass and it has some sort of elevation, we can say presented by Z, then that particle has potential energy. In fluid flow, the potential energy can be understood in terms of gravitational potential energy and pressure potential energy. Now let's first discuss gravitational potential energy. Now it is given by potential energy is equal to weight times elevation. Now remember that when a particle, maybe a particle of fluid, has some elevation z, with respect to some reference level, it will have potential energy. Now, gravitational potential energy is given by weight times that particular elevation. Remember, weight is the result of the force that gravitation exerts on a particle. Now, the same thing I did here by finding my kinetic energy with respect to unit weight, I will do the same thing with my potential energy. Now, potential energy per unit weight will be equal to my Wz, which is weight times elevation over weight. Now, even here I had weight, I just substituted it with specific weight times volume. Now here I will put my weight so that these two can cancel out each other, and my potential energy with respect to unit weight is equal to Z, which is elevation. Now, if I have my particle of fluid here, that was Z elevation. Whatever elevation I had here, 20 meters, 50 meters, that would be my potential energy. Elevation is in meters also, just as I had with my kinetic energy. On the other hand, pressure potential energy is associated with the pressure at a particular point in the fluid. Pressure is given by specific weight times height. Now, this height, h, is elevation with reference to a data. So, with respect to fluid, this elevation, we are going to take the depth of fluid. Now, this depth of fluid is going to produce its pressure. Now, that is to say, the deeper you go, let's say in a body of water, the more pressure you will feel. This is given by H. We are going to call this pressure that's being induced by depth pressure head. Now, this pressure head given by H is equal to pressure over unit weight of the fluid particle. Now, the total potential energy of a fluid element can be expressed as the sum of these two components: gravitational potential energy and pressure potential energy. If you take the entire energy in steady flow of a fluid element by combining the potential energy and the kinetic energy, you will have the kinetic energy plus the gravitational potential energy plus the pressure head. Now, this is constant for incompressible flow. Now, we will discuss Bernoulli's equation in further videos, but remember that in this equation, P represents pressure, V represents velocity, and Z represents elevation, height above a reference level. If you want, you can substitute your gamma with density and gravitational acceleration. Remember that with Bernoulli's equation, it is only valid under certain assumptions, such as steady flow, incompressible fluid, and neglecting energy losses due to friction or other dissipating mechanisms. Now, if we do flow of a real fluid in a pipe system, you will see that we will start to introduce energy losses. The other type of energy that I have not included here is called internal energy. Internal energy refers to the energy associated with the microscopic motion and interaction of fluid molecules. It includes both the kinetic energy and the potential energy arising from intermolecular forces. Now, in many cases, we often consider fluids as incompressible and assume that changes in elevation are small compared to the characteristic length of the flow. And in such cases, we can simplify the energy equation by neglecting potential energy changes. That brings us back to the Bernoulli equation. But as far as energies in a steady flow for an ideal fluid, that's a wrap on our discussion. We covered kinetic energy, potential energy, and I mentioned the internal energy as well as the Bernoulli's equation. Understanding these concepts is crucial for analyzing fluid behavior in various engineering applications, from designing pipelines to understanding the dynamics of airfoil shapes in aviation. I hope you find this video helpful. If you have any more questions or want me to cover other fluid mechanics topics and hydraulic engineering, please let me know in the comments. Don't forget to like and subscribe and stay updated with more exciting content. Thank you for watching. I'll see you next time.